Yeah, so in this question, they're giving us two flasks of volumes V1 and V2. So we've got two containers. And it tells us immediately after that that V2 is greater than V1. So we know that the second flask is larger than the first flask. They contain the same number of helium atoms at the same temperature. I'm not sure if it's relevant that helium is the sample rather than some other gas, but it does tell us we're dealing with helium. So it says compare the root mean square speeds and the average kinetic energies of the helium atoms in the flask. So the first thing you recognize there is anytime you're asked about the average kinetic energy, the only thing that matters is the temperature. Doesn't matter what state they're in, gas, liquid, solid. Doesn't matter what the substance is. It doesn't matter about the volume or the pressure or anything else. The only thing that matters is the temperature. So if these two gases are at the same temperature, they have to have the same average kinetic energy. That's what temperature is measuring. The average kinetic energy, which includes all three types of motion: translational motion, vibrational motion, and rotational motion. So that part is straightforward. We can answer that quickly. The root mean square speed is part of the kinetic energy. The kinetic energy has to do with the mass and the root mean square speed. Both of those are important. So if they have the same average kinetic energy because they're at the same temperature, and they have the same mass for the individual atoms because they're both helium, then they have to have the same speed. So if one has nothing to do with the volume of the container, it has to do with, on average, thinking about those individual particles as the individual particles are flying through space. On average, the energy of those particles associated with their motion, their kinetic energy, has to do with how fast they're moving and how heavy they are. They're at the same temperature. They have the same average energy associated with that motion. And so if they're at the same temperature, and they had the same mass, they had to be moving at the same speed. If they had the same mass but were moving at different speeds, they wouldn't have the same energy. So comparing these, we can say this is the same for both, and this is the same for both. So then the second part says, compare the frequency and force with which the heliums collide with the walls of the container. So I've got some helium in here. It says I have the same amount of helium. So the second part is asking about the collisions between the helium and the inside of the container. Why do we care about the collisions between the helium and the inside of the container? Right, that's what pressure is a result of. Pressure results from those collisions. So if I have a container that's made out of glass or whatever it's made out of, the material that container is made out of will probably only be able to withstand a certain amount of pressure before it breaks. Even though each individual atom or molecule is super tiny, and when it collides it doesn't really create much force, when I have a lot of those and they're all bouncing around, that force really adds up, and that's pressure. And if the container is not designed to withstand a huge amount of pressure, it might break. So I need to Right? Pressure is really important when you're dealing with the gas. So the frequency, let's talk about that first. The frequency of the collision, will that be different from one container to the next? Yeah, well, the key difference is, or the key thing to keep in mind is that the same amount of helium in both. So if I have 5 atoms in this one versus 5 atoms in this one, the one with less space, less surface area, those 5 atoms, as they're bouncing around, they're going to be colliding more often with the inside of the surface. If I imagine a really huge container and those 5 atoms are just moving through space, and they might collide with the wall once in a while, and then they'll bounce off of that and collide through space again. It'll take a long while before they meet the wall again if it's a really big container, right? So the bigger the container, the less frequent the collision. What about the force? Well, yeah, it's kind of not totally clear in the question what they're really looking for. Are they looking for the net force of the collisions overall combined, or are they looking for the force that one individual molecule would have? So because the molecules have the same mass, they're all helium, and they have the same speed on average, the average force of an individual collision is going to be the same. But if we're looking at the net force applied to the inside surface of the container, which is what the pressure is resulting from, then the net force is going to be more in the smaller container because I've got more collision. So over time, there's a greater quantity of force applied on the inside of that container because of a greater number of collisions in a given period of time. Questions about that? All right, so in part B, we're changing up the situation. We have equal numbers of helium atoms in the two flasks that are at the same volume, but the temperatures are different. So let's think about part B. Try to make a second flask with the same volume. That wasn't bad. In this case, I have equal numbers of atoms. They have the same volume, but T1, well, T2 is greater than T1. So this is a higher temperature. This is a lower temperature. So what about the root mean squared speeds here and the kinetic energy here? So we can say that let's call this T1 and T2. Again, kinetic energy, or average kinetic energy, I should say, only depends on temperature. So whatever's at a higher temperature, T2 has greater average kinetic energy. Again, that's regardless of what the substance is or what the volume of the container is or any other property of it. Temperature is the only thing that affects the average kinetic energy. And so, as we said, kinetic energy is affected by the mass and the speed squared. So if they have the same mass, but one has a higher kinetic energy, it must be higher because the speed is higher. So we can also say that the root mean square speed is greater for the one that's at a higher temperature. What about the frequency and force of collisions here? Well, they have the same number of molecules, same number of particles, same size container, but if these ones have a higher speed, they're moving through space faster, once it collides, if it's moving faster, it'll make it to the wall again and collide again in a shorter period of time. So I get a greater number of collisions, more frequent collisions at a higher speed. So the frequency of collisions goes up and the forcefulness of the collisions goes up. If they're moving at a faster speed, when they hit the wall, they'll hit harder. So the average individual collision will have more force, and I'll have a greater net overall force applied to the surface of the inside of the container as well. And then in the last part, just talk about that real quick. In part C, it says we have equal numbers of helium and neon. So here we've got one that contains helium and one that contains neon. They're in two flasks with the same volume. The temperatures are the same, 74 Celsius for both containers. And then it says comment on the validity of the statement. So 1, the root mean square speed of helium is equal to that of neon. Is that correct? So it does say they're at the same temperature, so they have the same kinetic energy, but they don't have the same mass. Right? An individual helium or an individual neon atom, if you look at where it is, its mass on average is about 5 times greater than helium. So if this one's 5 times heavier, if they were moving at the same speed, the heavier one would be able to collide with more force because it's got more mass. And it would have more energy as a result. So the only way to get them moving at the same speed would be is if the neon were at a higher temperature. But it's not. So if they're at the same temperature, they have to have the same kinetic energy. So if one is heavier, it has to be moving slower than the lighter one that's moving fast to be able to have the same kinetic energy. So when that statement says the root mean square speed of helium is equal to that of neon, that's not correct. Helium is going to have a greater speed. The second statement says the average kinetic energies of the two gases are equal. That is true. They're at the same temperature. Their average kinetic energies got to be the same.